Okay, so let's continue with the regular solution model. And in particular, we want to now ask, what does this all mean, right? So we have an expression for our free energy of the regular solution model, which has a first part that's just taken from the ideal solution model. So it's just xa natural log of xa plus xb natural log of xb, right? That was our free energy from the regular solution model. But in addition, it has a new piece that also is that's not proportional to RT, that goes like plus B12 XA XB. Okay. So now what happens when we look at what this does? So let's just sketch out what the contributions are to G. So I'm going to draw some axes here. So here we're just plotting energy, or contributions to this free energy, as a function of xb. So let's say this is xb. So this is pure A over here, pure B over here. So there are two contributions to this. We know there's, so this, and this is probably better written as delta G, right? So this is the delta G of mixing, right? So there are two contributions to the delta G of mixing. There's T times the, I should say, let's see, this N multiplies both of these. Okay. So we have T times the entropy of mixing, right? So this, we can think of this as T delta S of mixing plus the delta H of mixing, right? And the delta S of mixing is positive, right? The entropy is highest in the middle, it's 0 on the end, so this is our delta S of mixing. Our delta H of mixing is typically, well, can have either sign. It depends what sign we have for B12. So here we're going to consider the case where B12 is less than 0. And what does that mean? Now remember, B12, right, is equal to Z times Avogadro's number over 2 times 2 epsilon 12 minus epsilon 11 minus epsilon 22. So what B12 being negative means is that the energy of making like bonds is less than the energy of making unlike bonds is less than energy of unlike bonds less than energy of like bonds. Okay, so in that case, since the energy is lower, or let's say energy of unlike bonds is lower than energy of like bonds, so it would like to make unlike bonds. Unlike bonds preferred, right? So both entropy and entropy, both enthalpy and entropy, are driving you to mix. So delta H mix in this case is going to be negative because the contribution here is negative. And so delta G mix, because both, sorry, this is minus T delta S, both the contribution from the enthalpy and the entropy are going to be negative. Right. Okay. Now, but interesting things happen if we consider the other case, which is the case where B12 is greater than 0. So in this case, energy of unlike bonds is higher, and so enthalpy favors unmixing. So in this case, we still have the same shape of delta S mix, because that's coming from our ideal approximation, but we have a positive contribution from delta H mix. And that means that depending on how big this is, how big the contribution of delta H mix is to T times delta S mix, so depending on the temperature, you can either get a delta G that looks like we had before. So this is particularly true at high temperature. So at high T. But at low T, you can get a situation where delta H mix dominates at intermediate compositions, and so this is delta G mix at low T. Okay. So at what T do things change? Do things change from favoring mixing to favoring demixing, right? Because in this situation, you have lower free energy when you're not in the center, when you've formed compositions off stoichiometry or off center. So so if we think about as we change T and go from one curve to the other, at some point we go from having one minimum to having two minimum, right? So what we want to do is look at the derivative of delta G mix with respect to the composition, let's say XB, right? And so we can write this first in terms of just XB, right? So if we write delta G is equal to N times RT, and we could write this as 1 minus XB natural log of XB plus XB, or 1 minus XB, plus XB natural log of XB, plus B12, 1 minus XB times XB, right? So we take now the derivative with respect to XB, and we get N times RT minus natural log of 1 minus XB minus 1 plus natural log of XB plus 1, and then we get plus B12, 1 minus XB plus B1, or minus B12 XB. Okay, and so we can see these signs cancel, so we get N RT minus natural log 1 minus XB plus natural log of XB plus B12, 1 minus 2XB. And then we can take the second derivative, and that gives us N times RT 1 over 1 minus XB plus 1 over XB plus or minus 2B12. And so multiple solutions here exist when, for the first time, when we have a situation where the second derivative is equal to 0. right? Because that's the point where the curvature, there's some point where the curvature is equal to 0. Right here, when we're at high temperature, the curvature is uniformly positive. Here, when we're at low temperature, the curvature goes from positive to positive, so there must be some point along the way where it's 0, and so that's our condition for being able to have these two phases. And that happens when, so we can set this equal to 0, that happens when RT when 2b12 times xb squared minus 2b12 xb plus RT is equal to 0, and that happens when the temperature is less than b12 over 2R, which we call the critical temperature. So less than the critical temperature, we have two minima, and higher than the critical temperature, we'll have just one.